Okay, so just to remind everybody, here we are, and we're trying to characterize the bonding that is happening within the ethene molecule. And the ethene, if you remember, is the carbon to carbon double bond, with each carbon also having two hydrogens. So first it forms, it uses its sp2 hybridized carbons that also have a extra p orbital that extends above and below the plane of the carbon, plane, if you will, with the sp2 hybridizations being within the carbon plane. And so when it double bonds to another carbon that has the same sp2 and p orbitals, and all carbons do, then what we are going to see is an end-on-end axial bond that occurs between two of the sp2 orbitals, and that's going to make our sigma bond. And then we are going to have each of the hydrogens bond on to the other ends of the other sp2 orbitals, also making sigma bonds. But in the formation of the pi bond, remember we have one sigma and one pi bond in a double bond. In the formation of the pi bond, we have a side-to-side or parallel bond between the two p orbitals. And so that's what we're trying to characterize and show you. And so we need to be able to talk about these orientations. So once again, the end-on-end axial bond is the sigma bond, and the parallel bond is the pi bond. Okay, we're going to move ourselves ahead right now, and there, and we're going to go on. So we've kind of talked about this whole thing here. So if I redraw it again, and I think I am going to redraw it again so we can do some comparison here. So let me go ahead and redraw, and this time I'm going to flip it back around again because I draw so much better if I can flip it around. So each carbon has 3 sp2 hybridized orbitals. And they also have, each carbon also has a pi or p orbital that exists above and below the plane of the carbon. And so if I have two carbons that are wanting to bond to each other in a double bond ethene sort of format, I would have those two carbons existing or bonding first in an end-on-end orientation, making a sigma bond, and then in a parallel orientation, making a pi bond. So there's my pi bond, just like that. And my sigma bond is this end-on-end notation here. Okay, so it becomes pretty obvious when you are looking at the double bonding as compared. So this is my ethene. Now, if we compare it to an ethane, and remember that's going to be two carbons, CH3 single bonded to another CH3. So you're still going to have the sp2 hybridization, and that pi bond is still going to exist. And I'm going to draw that with a different color so you can see it. That pi bond is still going to be, p orbital. Whoops, I'm messing that up. That p orbital is still going to be there. It's just not going to be in use. So in ethane, what you're going to have is this end-on-end sort of orientation of the sigma bonding. So there will still be sigma bonding in ethane. There will be one sigma bond, but in ethene, there will be one sigma bond and one pi bond. Okay, so we need to talk about what the relationship is here. So if this is ethane and this is ethene, then the bond strength in ethane is for a single bond, and it's going to be less than the double bonded ethene. So bond strength single bond will be less strong than the double bonded ethene. As you know already, single bonds are longer, double bonds are shorter. Okay, bond angles. Our bond angles in the ethane are going to be 109.5, whereas in the ethene it's going to be 120. Our geometry in the ethane is going to be tetrahedral, and our geometry in the ethene is going to be trigonal or trigonal planar. And then the rotation yes, can happen in the ethane because all you have to do is twist around the single bond. But in the double bond, you can see now there's some above and below the plane of the carbon, so there will be no rotation in this part here. So far, any questions? That might be a good summary right there of what is going on. All right, you're going to need to speak up if you do have any questions so far. Right, the pi bond is inhibiting the rotation. Okay, thank you. That was a good question. All right, here we go. Okay, so now we need to talk about this idea of what is cis-trans isomerism in alkenes. Okay, so many times we are having the isomers of alkenes, simply they are based on the position of the groups that are attached across the double bond. So due to the restricted rotation at the C to C double bond, so since we've already established this restricted rotation, we will definitely have two different formats that we are likely to see in an alkene. So here is our first alkene where it has, let's just use some chlorines here, two chlorines on the same side of the double bond. And this format is called cis. Cis means same. And then we have the trans format, which means across. And so we will have C double bond C, and the chlorine will be on opposing sides, just like this, of the double bond. Now, it is possible that you could have two chlorines on the same carbon of the double bond, but that is not what cis and trans is referring to. Okay, so they're called stereoisomers because of their positioning of compounds around the two carbon double bonds, but they are not readily interconverted by rotation. In other words, you'd have to break the bond to rotate them. Okay, and so it's talking about breaking the pi bond here. These are configurational isomers, and they can be separated by distillation. In other words, they have a difference in boiling points. So for cis-trans isomerism, each carbon of the double bond must have two different atoms or groups attached to it. So that's a good thing to remember. Each carbon of the double bond must have two different atoms or groups attached to it. And then we talked about what those two things mean. So we should add in here, well, how do we name this? So let's make sure that we can name these two that I've drawn here. The first one would be called cis. Oh, not yellow, not yellow. Let's get our pink. There we go. The first one would be called cis, and then we use the dash. And then we're going to use the positional numbers, 1, 2, dash, dichloro, and then we would say ethene. Now, if this had a different length of carbons, then you would have to add in the number in between chloro and ethene to say where the double bond is. But you determine, you're determining what side of the double bond the chlorines are found on by using the terminology cis. In the trans, you are using the terminology trans dash 1, 2 dash dichloro and ethene to represent where the chlorines are located. In other words, across the double bond from each other. I think we're getting really close to the end of our notes for today. Does anybody have a follow-up question on this particular format of naming these two isomers? Most of the time I have never seen them capitalize it. In fact, they italicize the cis and trans. So a lot of times it gets written with that kind of leaning to the side kind of format. Usually it's a little bit leaning to the right, if you know what I mean by italics. So usually you don't. Usually if you're going to capitalize, you begin at the die. Okay. All right. Thank you. That was a good question there too. Okay, I think I'm pretty close to the end of my notes here. Let me just check a little bit more here. All right, yeah, we're going to stop right here because we will be doing addition and substitution reactions next class period. So let me go ahead and stop my video.